In this video, we will be talking about evaluating limits analytically. Before we do that, I want you to recall a couple of things. The first is just what we covered last video, and that is basically what a limit actually is. So from the last video, we determined that a limit, as x approaches c of f of x, gives the value that f of x approaches from both sides of x equals c. So what this means is we're just exploring what happens when we get infinitely or arbitrarily close to x equals c on our graph. And I think the best example that kind of caught this in our last video is this example over here in blue. Okay, so we wanted to find the limit as x approaches 1 of x cubed minus 1 over x minus 1. So when we graph this, we got this graph down here, and we notice that nothing actually happens at x is equal to 1. But if we just follow our graph from both sides, if we were to continue that trajectory, we would get that our output is still 3. Therefore, this limit is 3. So again, it's what's happening along the graph as we get super, super close to what we're asking for the limit to be. The next few things I have here are things that you've learned in previous years. So the first is just the factoring of polynomials. And the better you're able to do this, the better luck you're going to have with limits. Okay, so the example I have here is x squared plus x minus 6. And in order to factor this, we are looking for factors of -6 that add up to positive 1. And the factors that do that are plus 3 and minus 2. Okay, so our factored form of this polynomial is x plus 3 times x minus 2. The next thing I have on here is rationalizing fractions. Okay, and normally when we think about rationalizing fractions, we're talking about getting square roots or imaginary numbers out of the denominator. Okay, and in order to do this, a lot of times we're going to be multiplying by conjugate. Okay, so in this example that I have down here, we have 4 over the square root of x minus 2. In order to rationalize that, we have to take the conjugate of the denominator and multiply that by the numerator and the denominator. So the conjugate of the denominator, square root of x minus 2, is just the square root of x plus 2. And when we distribute that in the numerator and FOIL that in the denominator, we get something that's a little bit more rational in the denominator. The thing I want you to take out of this, though, is what a conjugate actually is. So if we have sum a plus b, the conjugate of that is a minus b. And when you multiply those two things together, you cancel out a lot of things and make life a little bit simpler. Okay. The third thing I have on here is rational functions. Okay. And a rational function is just a function whose numerator is some polynomial and whose denominator is also some polynomial. And I'm using this notation because this is going to be used in a later theorem, and this might just clear things up. And next is our objectives. So we want to evaluate limits using properties of limits, so we're going to be going over a couple of properties. And we want to go over how to evaluate a limit using the dividing out technique and the rationalizing technique. So in the last video, we learned that the limit as x approaches c of f of x does not necessarily depend on the value of f at x equals c. So it's not necessarily just f of c. You don't just plug it in, right? And again, one of the better examples that caught that is this same example from above. Okay, so the limit as x approaches 1 of x cubed minus 1 over x minus 1. If you were to plug in 1 into that function, you wouldn't get anything because that would make the denominator 0 and then it wouldn't exist. Okay, but our limit is still 3. However, sometimes the limit as x approaches c of f of x is actually just f of c, right? So that is possible. And they can be evaluated just using direct substitution. All right, these functions are said to be continuous at c. Okay, so the most basic example of that is just the line y is equal to x. So if we take the limit as x approaches 2 of that line, all we really have to do is plug in 2 for x, and we get our answer. Because the graph, as it approaches 2, becomes 2 as we get closer and closer and closer. This graph is also continuous at 2 because this point does exist. Okay, up above, this graph is not continuous at 2 because that point does not actually live on the graph. It does not exist. So in this video, we'll be talking about functions of that latter part. So functions that are continuous on C. All right, and those functions have some properties that can help us evaluate different limits. All right, so our first theorem, it just has to do with some really, really basic limits. All right, so let b and c be real numbers and let n be a positive integer. From those two assumptions, if we have the limit as x approaches c of some constant b, that's really just equal to the constant. Nothing happens. Okay. The second one is the limit as x approaches c of x is just c, right? So we'd plug in c into this x, and then we'd get our output. And then the third is if the limit as x approaches c is x to the nth power, again, all you do is plug in c into x, and you get our output. So some examples of those, I realize those aren't the most concrete things. First, if we have the limit as x approaches 2 of 3, because we're just evaluating a limit of a constant, it's just that constant. The second example is the limit as x approaches negative 4 of x. Again, because lines are continuous at all points of C, we just plug in negative 4 into x, and we get our output. And then the same is true for x squared, right? So the limit as x approaches 2 of x squared, we would just plug in 2, and we'd get 4. Because quadratics, x squared, is continuous on all points of C. So these are the most basic limits. All right, but then we get into a little bit more in-depth stuff. All right, so before we get into these, we have to let b and c be real numbers, and we have to let n be a positive integer again. And then f and g are functions with the limit as x approaches c of f of x be L, and the limit as x approaches c of g of x is just k. All right, so we're just defining the limits of those two functions as L and k. All right, so the first property of limits is the scalar multiple property. All right, so what this says is that if we have a limit of a scalar multiple of a function, right, in this case b, we can just take that constant out and evaluate the function as is. Okay, so the limit as x approaches c of b times f of x is really just b times the limit as x approaches c of just f of x. And then again, if we just substitute what the limit actually is, which is L, we would just multiply b times L. So again, if we have a constant inside a limit that we can factor out, we can actually just drag that out front and ignore it for a second. The next property is the sum or difference property. And what this says is if you have the sum or difference of two functions, you can actually separate them into different limits. Okay, so the limit as x approaches c of f of x plus g of x, we can actually write that as the limit as x approaches c of f of x plus the limit as x approaches c of g of x. And again, if you just substitute those limits for what they're actually equal to, you just get L plus k. The next is the product property. Okay, so this says that if you have the limit of a function times another function, again, f of x times g of x, you can just separate those as the limit of one function times the limit of another. So again, as the limit as x approaches c of f of x times g of x is really the limit as x approaches c of f of x times the limit as x approaches c of g of x, which again, if you substitute, that's just L times k. The next is the quotient property. So just like the product property, if you have the limit as x approaches c of the quotient of two functions, you can just split that up into the limit in the numerator and the limit in the denominator. So the limit as x approaches c of f of x over g of x is really just two limits. The limit as x approaches c of f of x and the limit as x approaches c of g of x. And again, if we substitute in for what they're equal to, we just get L over K. The next is the power property. Okay, so this says that if you have the limit as x approaches c of some f of x to the power of n, you can ignore that n for a second, take the limit, and then take that limit to the exponent. Okay, so the limit as x approaches c of f of x to the power of n is really the limit as x approaches c of f of x. You find that, you evaluate that, and you take that number to the nth power. So again, if we were to substitute what's inside these two parentheses, we would get L to the nth power. So using these properties, I want to go over a couple of examples. The first is the limit as x approaches 2 of 4x squared plus 3. And in order to do this, there's a couple of easier ways, but I want to split it up into a couple of different limits just so you can see how these properties actually work. All right. So because we have a sum of two things, we can split it up into two limits right off the bat. So the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. Okay, this second limit is just the limit of a constant. So this is just equal to the constant inside, which is just 3. And then this limit right here, we can actually take out the 4 and factor it out, right? Because that's a scalar constant, a scalar multiple of x squared. So then this is 4 times the limit as x approaches 2 of x squared. So then we would just plug in 2 into x squared, and this would be 4 times 2 squared, which is just 4, which is equal to 16. Okay, so the first limit is 16, the second limit is 3. We add those two things together, and we just get 19. The second limit, the limit as x approaches 1 of 2x minus 3 over x plus 5. Again, we could just write that as two limits using the quotient property. So that's the limit as x approaches 1 of 2x minus 3 over the limit as x approaches 1 of x plus 5. And again, because this is continuous, we can just use direct substitution at this point. So we would just plug in 1 into each of these functions on the numerator and denominator. So we would get 2 times 1 minus 3 over 1 plus 5. So we get negative 1 over 6. And then the last one is a little bit trickier, and I wanted to use the power property. Okay, so the limit as x approaches 3 of the square root of x plus 1. I'm going to rewrite this as the limit as x approaches 3 of x plus 1 to the 1/2. And the reason I'm doing this is because of the power property. So we can actually ignore this 1/2 for a second and put it on the outside. Then we can use direct substitution in the inside. So everything inside these parentheses, if we just plug in 3, we get 4. 4 to the 1/2, or the square root of 4. that's just equal to 2. So again, we can use these properties to simplify things a lot more. Again, sometimes we don't have to simplify everything everywhere we see it, but those properties are there to help you simplify maybe harder problems into a couple of simpler ones. So the last two properties we need actually make our lives just a little bit easier. And this is theorem 1.3, the limits of polynomial and rational functions. What these say is that if you have a polynomial or rational function and you're taking the limits of that, really all you have to do is plug in your constant c and then get an output. Okay, so the first part of this theorem says if p is a polynomial function and c is a real number, then the limit as x approaches c of p of x. In order to find this limit, all you have to do is plug into c into your polynomial. Okay, so your answer would just be p of c. And I actually used this above in the last couple of examples. The limit as x approaches 2 of 4x squared plus 3, that 4x squared plus 3 is a polynomial. Okay, so really I didn't have to go through all those steps. I could just plug this 2 into x squared and then evaluate from there. Okay, so if you do that, you get 4 times 2 squared plus 3. Again, you get 16 plus 9. Sorry, plus 3. Which just equals 19. Okay, so again, this just saves just a little bit of time. The second, if r is a rational function given by r of x is equal to p of x over q of x, and c is a real number such that q of c is not 0, then the limit of our rational function, in order to find that, you really just, again, plug in c into your function r, which if you want to take it a step further, you could just plug it into the numerator function and the denominator function and get an output. So an example of this is the limit as x approaches 1 of x squared plus x plus 2 over x plus 1. In order to evaluate this, the first thing we have to do is we have to plug in 1 into our denominator. And if it equals 0, there's some things that we have to do extra. But because this function's denominator is not 0, when you plug in this 1, you can plug it into the numerator and the denominator and just get an answer. Okay, so this would just be 1 squared plus 1 plus 2 over 1 plus 1. So when we evaluate that, we get 4 over 2, which is just 2. The important part here is that if you have a c that makes this denominator 0, then you have to have a couple more steps. If you don't, though, you could just plug in your c value and get an answer. When we do have q of c that is equal to 0, there are a couple of things we can do. Okay, with rational functions of the form p of x over q of x, again, like just above, when q of x is equal to 0, we can either find a greatest common factor between the numerator and denominator and divide those out, or we can rationalize. Okay, so the first thing I want to focus on is the dividing out. And for an example, I have limit as x approaches -3 of x squared plus x minus 6 over x plus 3. And from above, you might think that we could just plug in this -3 and get an answer. But this -3 makes the denominator equal to 0. Okay, so in order to combat that or get around it, what we can do is we can find a common factor between the numerator and denominator. And the best way to do that is to factor the numerator and hope that our denominator has a common factor with it. Okay, so if we factor x squared plus x minus 6, which I actually did in the recap, we get x plus 3 over x minus 2. And again, this x plus 3 stays the same. Now, if you notice, the numerator and denominator do have a common factor, x plus 3. So we can actually cancel those out, and we're just left with x minus 2. Okay, so then our limit is actually a little bit simpler. It's just the limit as x approaches negative 3 of x minus 2, which we can just plug in to x and get an answer. Okay, now if we looked at this on a graph, if we graph this on a calculator or Desmos, we would get a line with a little hole right at x is equal to negative 3. Okay, and again, if we continued our function through that empty point, we would get that our output is still negative 5. And again, if you made a table of values and got infinitely close to x is equal to negative 3, the same would be true. It would still be negative 5. The other option when our denominator is 0 is to rationalize the numerator or denominator. Okay, so in this example, we have the limit as x approaches 0 of the square root of x plus 1 minus 1 divided by x. Okay, and before we do this, I do have a couple notes to the right. That's for you. I'm not going to go over those explicitly right now, but I am going to be using some of those terms. Okay, so the first thing that I would do again is to just check what happens at our limit. So if we plug in 0 into our denominator, we get 0. Okay, so that would signify that we have to do something different. Okay, and in this case, because we have something irrational in the numerator or denominator, we can try and rationalize one of those two things. And because our only irrational piece is in the numerator, we'll try to rationalize the numerator. Okay, and in order to do that, we need to multiply by the conjugate of our numerator in both the numerator and denominator. Okay, so what that means is that we have square root of x plus 1 minus 1 divided by x, and we're multiplying that by our Klepper form of 1, which in this case is the square root of x plus 1 plus 1 over itself. And again, just to highlight, this piece would be our a, and this one would be our b. In order to find the conjugate of those two things, we just change the middle sign, which becomes positive. Okay, and because we're multiplying that on the numerator, we have to do that on the denominator. When we FOIL the top, we get x plus 1, and then minus 1, and then we get x times square root of x plus 1 plus 1. When we simplify that a little bit, we just are left with x in the numerator, and we're going to keep the denominator the same. Then you can see that there's a common x in the numerator and denominator, so we can cancel it out. And we're just left with 1 over square root of x plus 1 plus 1. Okay, and before I go any further, I wouldn't expect you to be able to do this right this second, but this is something in the near future that would be manageable. Okay, so once we get to this step, then we can take the limit as x approaches 0. When we plug in 0 into our denominator is not 0. Okay, so when we do that, we get 1 over square root of 1 plus 1, which is just 1/2. And then that's our answer. Again, you have to be a little bit clever here. And again, I'm not expecting you to do it right this second, but this is a technique that can help you out later on. We can also verify this on our graph. So if we were to go to our graphing calculator or Desmos and plug in our function, we would get something that looks like this. okay? Or we could make a table of values and get closer and closer to 0. But if we were to continue our graph, we would get closer and closer to 1/2 and then cross it. Okay, so that just verifies our original answer. So to recap all this, I wanted to just put everything in one place. All right. I get that this is a lot. There's a lot of properties. There's a lot of different techniques, and limits in and of themselves are new to you right now. So I wanted to leave this up for a second and give you a chance, if you need them all in one place, to have it. But a couple things that we went over. We went over basic properties of limits. Then we went over some more in-depth properties that deal with multiplication, sums and differences, products, quotients, and powers. And then we went over 2 techniques to use if our limit doesn't exist or we can't directly input our limit into the function. Okay, so that's dividing out and rationalizing. All right, so that's all I have for you for now. Thank you for watching.